Hello guys, today is Space and Times number 7. Okay, and the name of today's is Forces and Curvatures. Forces and curvatures. Force, something that you at least a little understand, a little more maybe with this Newton's law. Newton's laws. Curvature is when this something is curved, right? The space-time or space, whatever, it's curved. The first question, any questions on the previous lecture? No, everything's okay. And guys, when you're talking, talk louder because it's difficult to hear you. You know, very difficult to hear. I don't know. The previous time was louder. I don't know what.
Hold on a second. They're moving closer.
Yes, please. Okay. Hello again.
Papa said that we couldn't find the time to actually do the questions.
We'll do them.
No, I know the questions. I said I know that. I asked about, do you have any questions on the previous team?
On the standing waves.
No.
No. Okay, good then. So we'll now continue. And today we'll talk about force and curvatures. I told already that the modern physics is in a certain way, it is called forceless. So there are no forces. So forces are something from the ancient times that came from Newton times. Newton physics was physics of forces, right? And forces, and as you know, forces, they cause acceleration, the change of velocity, right? Change of movement. And modern physics is actually physics of curvatures, not of forces. So the curvatures somehow stand for the force. So how it happens? In a certain way, we talked about that, right? But today we will talk on this a little more to understand certain things. Okay. So first of all. Let's talk about this time loop. Remember that quantum is actually a loop in time, so it's a circle. But time, according to the theory of relativity, time is space. Actually, space is time. This is just two sides of the same thing. So when you have loop, like for example, you have point 0, right? And now you're moving somewhere, then you maybe come to the point 1, and then you return back. So this is like time, and this, when we remember, we call it anti-time, right? Or space. Yes? Yes?
I thought this was called like a qubit or something like that.
Like a what?
A qubit.
Okay, you may talk about this, yes, but qubit is actually, qubit comes from quantum mechanics. And quantum mechanics is, believe it or not, is based on the loops in time. It's not fully accepted in modern physics, but it's inevitable. So qubit is a state, is a quantum state. So the matter can be in this state or another state. And this name of this state, the name is qubit. So qubit is actually sort of a quantum in a certain state. That's all. It's connected with the information. We'll talk about information later. We talk a little about it before. They're just touched a little. Information has a very close connection with this probability thing. Remember these probabilities, chances, and everything. Interesting enough that information has a lot to do with the probabilities. And also it is something that looks like that information is not matter, but it is closely connected to matter. So close that actually there are formulas that actually connects energy, directly connects energy. I can write it right now, just it's out of today's lecture. It directly connects energy with information. So information, when to get information, you have to spend certain energy. You cannot get information without pushing somewhere some energy. And again, when you use information, actually, it gives you sort of an energy too. That's very intricate thing, which is not well understood in modern physics, but it's still there. It's used widely. Like for example, in the quantum, not the quantum, like in any computer, right? You can erase information, right? Just erase something. Something is written in your computer, right? And you want to erase it, delete it totally, erase from memory, from everywhere. You have to put some information, some energy into it. And as a result of the putting energy, there are this energy goes into what's the name of this? Into thermal, into temperature actually. Как сказать теплота? Забыл. Антош, теплота.
Warm?
No, not warm. Okay.
Heat?
Heat, yes. Sorry. It goes into heat. So when you erase something in your computer, the computer gets some heat. And you cannot get rid of it. And there's a way how to not to do it. So you just not erase, but just move information from point A to point B in your computer, in your memory. So you point from one place to another. Just put it aside, right? And to that, you're not using too much energy at all. So there are interesting tricks connected with information. Information is very closely connected with energy. But this is just not this lecture. So returning to this loop, right? When we have loop in time and anti-time, and time and space are the same thing. So time is space, right? So this is time is anti-space, you may say, and space, anti-time is space. So when you go this way in time or back in time, at the same time you go in space one direction and in space in another direction. So the movement in time is connected with the movement in space. This is first thing. The other thing is that if you look that something is moving, right, from point 0 to point 1, right? So it is going this way, right? So it looks like that it is repulsed. It is a repulsion. So it looks like that point which is moving this way, it is repulsed. Repulsed, right? Correct?
Well, repulsion, yes.
Repelled or repulsed?
Repulsed.
Repulsed. So it repulsed from point 0 and goes to point 1. But when it returns back, because it's a loop, right, it looks like here it is attracted. It is attracted. And this is the point where repulsion change into attraction. So it is attraction. You see? Repulsed, attracted. And this is the point actually where the movement stops, right? It's here, it's no movement, and here too, because it went, it was going, then stopped, then goes back. And you know what it means. When you first going this way, and then you stop, what it means? That you are accelerated here, then accelerated with minus here, so there a brake, right? You push the brakes. And here again, you are moving this way with the negative acceleration, and then again come to a quiet position here. So you have not only movement, but also movement looks like repulsion and attraction, and also it has a lot to do with acceleration. You got the idea, right? So pretty simple. Just from go to here, if you go into the loop, it looks like that you're first going far from you, right? Then you brake, right? Then you turn back and goes again, and return here and brake again. So the movement in the loop looks like the movement can be continuous, just no stopping. It can be like this, goes and goes and goes. That's how it goes in quantum. The movement, the time is never stops. It goes in loops and goes and goes. But it looks like that it goes like vibration. So what it means that time loop has a lot to do with acceleration. And and you see that something in this curve, something is interesting. You know, there's a line, like a straight line, right? And there is a loop. And loop is already a curve, right? So the straight line is like broken somewhere here and goes back, right? And this is already not straight line, it is a loop. And loop have curves, at least here or here. Or you may say that the whole thing is curved. So what we're dealing here, we're dealing with the one-dimensional, so one dimension is one, right? One-dimensional curvature. In this picture, here is straight, no curvature. Like curvature usually is R. 0, and here is curvatures can be very big. Here too can be very big. So these are exactly points when the system is accelerated. So it goes with straight with the same velocity. Then it brakes and goes back, and again there's zero velocity here. So you can stop and then goes back. Or here it's maybe same velocity, but it looks like that it repulsed, attracted, and acceleration changes.
Can I ask you a question?
Yeah?
The loop above, is it a circle?
Yeah, it looks like a circle. I draw it like a circle, right? I've drawn it like a circle, but usually you cannot tell like directly is it a circle or not. In regular thing, in like all is equal, like yes, it is a circle. In other cases, can be not circle. Say it again.
So I'm asking is because in that case, if it's a circle, then in the below diagram, it will not be constant speed. It will be
yes, exactly. Constant speed on this interval from here to here.
It won't be constant speed there either, right?
No, in this it can be constant. Why not? From here to here, but not from this point. Here it accelerated, then velocity is not changed, then change it again here, and then here it's not changed again.
So it's not the same loop as above.
No, it's not. No, it's not. No, I agree. It's not the same. It's just pictures. I just pictures for you to understand how curvature is connected with the acceleration. And also you should understand that there is no real acceleration here. Interesting thing is that when the space-time is curved, there is no acceleration whatsoever. No acceleration. It looks like it's nothing changed, but at the end, because it is curved, at the end you comes to the certain place and you see that something is oh, Jesus Christ, okay. Something is not that simple.
I did it.
Okay? Any other?
No, I got one more question. I'm sorry.
Sure.
This loop, what are the dimensions? Is it just x and y?
Say again?
Space? Or
This is one, yes, because this is a line.
no,
Line has
no. No, what I'm asking is, so let's suppose we'll look at the loop above, right?
Yeah.
So going up, is it what? Is it just y and going right, left, sideways is x, and it's just space, basically? And there is something moving in the circle? Yes?
Yes, this is circle, like this is a loop in time, right? We can call everything time. The time. Time is a dimension one, time. That's it. One dimension. Nothing else. And time is running, like in loops, right? But because of when we look from certain frame of reference, like we look from certain place, so there is a difference when we're going out of point zero, right? When we started, right? Out, or we're returning back. There's some difference in this. And we call this difference, that the difference is, we call one direction time and another direction anti-time, or space. Space and time are the same thing, just two sides. Like this is one side, like maybe upper side, here is the lower side. Or two sides of the moon. This is light side of the moon, this is dark side of the moon.
And 0 and 1 are just two allocations
Just any locations. Any, yes,
So
any.
0 could be our house today,
Yeah,
and 1 could be our neighbor's house tomorrow.
maybe. Yeah,
And
you
we
may.
move from house to house
Yes,
time.
yes, yes. You may take it like that. And think about it too. It's not that easy. There are lots of questions here, but anyway. So we'll continue, right? So this is for loop and one dimension, right? So loop is one dimension. But nobody said that quantum, real quantum, is one dimensional. No. Actually, space-time, as you know, has 4 dimensions, right? Actually, I told you already, maybe you remember, maybe not, that actually time has at least 3 dimensions because it's the past, the present, and the future. Those are dimensions of time. And they're not only like dimensions like the word of it, no. When you use it as mathematically, it goes to, we talk about these quaternions, these objects, mathematical objects. And those quaternions describe very, very closely exact physics of the process. So quantum is not just a line in time. It is much more complex. And we'll talk about it a little more, okay? So look, for example, let's imagine that we have like a rubber membrane, right? Like this. It's a rubber. Like a part of a balloon, like a rubber balloon. You know, these fun balloons, right? And we hit it in the middle, somewhere here, of this rubber plane. What will happen, actually? It start vibrating, right?
Oh, and it will happen.
Uh-huh.
It will go down. Yes, then it will go down and the will go up.
What will do then?
The sensor will form a curve going downward.
No, if we hit it here, let's, for example, it's hold it here. You hold it there, like here, here, and here. And just like this goes. It's a rubber thing, like a part of balloon, right? Just part.
The sensor will go down.
No, you hit it, right? It goes down, but because it's elasticity, right? It goes up and start vibrating. You can do it on your balloon, like kick it, it will bang, right? So it starts vibrating here like this, and then the waves start going out. It's like waves on the lake. You may even see them if you have like a big balloon. You can see if you hit it. They are pretty fast, but they're going like this. So waves.
Would just the surface of water be a good example? If you
Yeah.
throw a ball,
Yeah,
it
the same
falls
thing.
up and down, and there will be waves.
The same thing. Yeah.
Anything like that?
So there are waves going from the center. When we hit it in the center, waves goes all directions, like
Oh, yeah.
on the surface of this rubber space, right? So this is dimensions of this space is 2. There's 2-dimensional space. 2 coordinates, 2 dimensions, right? So you may put coordinates like y and x, right? 2. There are 2 coordinates on this. So and dimensions are 2. So the waves going in 2 dimensions, right? So look at this picture. It looks like very, I don't know, pretty maybe obvious, right? In the case of that, if you have this wave, right? So this is the outer ring, so this out, right? And this is inner ring. You understand, right? And this is even more inner ring. So these 2 rings are inside this ring, right? And this ring, which goes out, it's outside of this ring. So you have relations inside and outside, or in and out, right? And the waves going from in to out direction. Very simple, right? Now let's take a little further. Let's go a little further. And we have a little more complex space. I forgot how to. I think it's Антоша, Тор, кажется, так, да, пишется? Thor?
Tor?
Тор, да, Тор.
I don't know. Yes, but I don't know what this means. It's a name.
Бублик, bubble. Ну, бублик, как это, донат?
Oh, Taurus.
Taurus, oh, just like donut, right?
Yes.
Так, donut. Okay, now we have this space with this donut.
That's a really fat donut.
Really fat donut, yes. And here's a donut
There's a
hole.
hole in the middle. You see that? That's a hole.
Here's donut hole. Inside donut. It goes inside donut, right?
Yep.
You got the idea?
That's pretty good drawing.
Okay. And let's, yeah. And let's, for example, okay. Let's first on this donut let there be Flatlanders. Flatlanders are people who live in 2 dimensions. There are no 3 dimensions. There are only 2 dimensions. So some guys who belong to the surface of this torus. This is this torus surface. It is a surface, like 2-dimensional surface.
Up and down.
One guy, another, here is another guy, right? They can go, but all they do, they're all in 2 dimensions. They cannot go out of this torus. They are only on surface. And imagine one of the guys, he was traveling, and he comes to this hole, right? And what he did, he put his head into the hole and he wanted to look. What's inside there? You understand, right?
Yeah.
So he comes close and look into this. And because they all belong to the surface, they are line of sight, how they see each other, it also belongs to the surface. The line of sight cannot go outside. There's there's nothing there. They belong to the surface. So when he looks inside, he looks exactly through this, you see? And it goes out, and then goes out, and what you see? You see this guy from the back. Do you understand the idea? The line of sight is curved and goes.
Oh, I get it.
You got it?
The line of sight is 2D, and the hole is curved. He sees the image, but it curves the image into a circle.
Yeah, the line of sight is curved too. Everything is curved here. So the line of sight is curved here. So what you see there, he looks, when he looks.
Can I ask you a question?
Sure.
Sorry to interrupt you. So the light here travels just on the surface?
Uh-huh.
Kathy, did you hear that? If the light travels on the surface, then the guy on the top, when he looks at the light that travels on the surface, the light that hits his eye would have traveled from the back of that other guy. Does that make sense now?
Like a photon. Okay, you see, maybe this guy, like maybe somewhere in this flatland there's a sun. The sun belongs to the surface too. Sun. The photon from the sun goes to this guy, reflect from him, goes here, then goes inside the hole, and he see him here from here. So the photon, the photon goes like this, and come to the eye of this guy who looks inside the hole. This hole doesn't actually look like for him like a hole. It's like a funnel, right? He can travel around, and you see that's all the ways goes down there. It's like a funnel goes somewhere. Actually, it is a picture of black hole. It is a 2-dimensional black hole. 2D black hole. This is a picture. So when you look inside, and the other guy can look like from here, right? Right? You look here, and he can see something here too, like here maybe, some other guy here. Whatever. Yes?
What would happen if you go inside of it?
Yeah, he will go. Okay, we can go inside. Yes, he can go inside, go through the hole, and went outside here, right? The same thing as photon.
But how would he see it?
So what?
How would he see it though?
How what?
How would he see it?
I didn't get the word. What?
How would he see it? I don't understand the question.
How would he see what the tunnel you go down? Because we see
He
it.
will not see a tunnel. He will not be able to realize it's a tunnel, huh?
You see the good lines?
No, you just see a plane going forward.
It's pretty weird picture that he would see. It's maybe pretty difficult to say. But if one of the things that you can do, you just try to picture it after that, right, and try to understand it, because one of the questions is exactly about that things. So you can imagine something what is going on there, what he will see when he goes inside, and all other things, because he can see also with this way too, like those two guys can see each other in this way, right? These lines, remember these lines, they are shortest lines. They are called geodesic or geodesic. They are the shortest lines. They are not straight lines, but they don't know that. For them, they are straight lines because they're shortest. So for this guy, this is direct picture of this. He'll see like this. Oh, here I go. He will be smaller, of course, because of perspective. You know, the perspective when he goes further, right? This guy will look smaller, but anyway, he will see it like right ahead of him if you look inside. So he'll see the guy here. The same thing for this guy. He will see somebody here or whatever. So for this Flatlander, so you see there are interesting thing here. So when you look inside, actually you see something from outside. These things, definitely, those guys are outside of this hole, right? Those guys. But he see them not only outside, but from the back also. So everything is inverted, right? So why I draw this picture? Because you can see that the understanding between inside and outside, they're very relative. The curved spaces gives you relative things, that something that was inside becomes outside, and back and forth. So inside and outside are very relative things. Just a little more about it. There's another interesting picture. I'm not talking. We'll not talk about this too much, but it is called Klein bottle. There's a guy, Felix Klein. And here's his bottle. Felix Klein was a famous German mathematician, and he worked a lot of curved spaces, and pretty famous in them. So he suggested some interesting like geometry, like this. So it goes. It's like actually it is a torus, but non-orientable. It's called non-orientable torus.
What's that mean?
I'll tell you. So this is the hole, the same thing as in the torus, remember? It goes like this, right? But instead of going there, it goes like outside. It like penetrates like through the surface, right? Curved like this. And goes like this. Do you understand what I'm talking about?
Nope. No.
So it's a bottle, right? Sort of a bottle. And this is the... Как там горлышко-то?
The neck.
The neck, yeah. So this is the neck of a bottle, but the neck is curved from inside goes, penetrates inside and goes outside. So in the torus, if you travel on the surface, like for Flatlanders, like if you travel on the surface of the torus, you cannot go on the other side of the surface. You're always on the side of the torus, on the upper side. Even if you go through the hole, you are not going like really out, really inside, right? But here, just watch. If a Flatlander, right here, Flatlander goes, and he goes inside, right? Now he goes inside on the inner side of this. Как это называется, горлышко? Throttle? Neck. Okay. Goes from inner side. He goes inside. And he goes all the time inside, right? But when he goes here, you see he suddenly appears outside. Because this is outside there, so he goes and he comes here. Look at this. This is called Klein bottle, and it is non-orientable because you can go on both sides. While traveling in this thing, you can go on both sides. Just compare it with the torus. I'm not going to talk a lot of this. Just imagine it, and Tosha, you know how to imagine this thing and to draw it. And there are some questions on this for you.
This is similar to Möbius. What's it called?
Yes, Möbius stripe, right? Yeah, similar to Möbius stripe. Yeah.
Like it's similar to Möbius strip. See, this is a Möbius strip.
By the way, this there's another interesting thing for this Klein bottle. There's a mathematical field which is called topology. Topology. This is all about topology. Topology is a science which actually researches the rubber surfaces, the surfaces they can expand, contract, and all that sort of thing. So this is topology. So topologically, this Klein bottle topologically is very similar to torus, but it's non-orientable. Has only one side, like a Möbius stripe, only one side. And the torus, the real torus, has two sides. So just think about it. Now we talk about goes a little further and talk about waves. Let's talk now about waves on some very simple surface, which is called sphere. Sphere, again, its dimension is 2, right? And like our globe, or our planet, right, is sort of a sphere, right? So like North Pole, and here is like somewhere on the other side, there is South Pole, right? South Pole. And then imagine that this is made of rubber. This sphere is made of rubber. Again, the same thing, like membrane, like a balloon. Rubber balloon. And imagine that you hit something here, like you hit this from there, right? There appears to be waves, right, which are going up, and the waves goes all directions from the South Pole, and the waves will have that kind of picture. They're going from the South Pole this way, right?
I'm gonna go to the bathroom and I'll be there.
You see? They goes from here. All the waves goes like this. If you hit it from there, and then they focus here, because here the circles are expanding and here they're contracting. So the waves goes out there, and then they focus on the North Pole if it starts from the South Pole. Again, if you hit it on the North Pole, they will first go this way, like a rubber membrane, right? Goes this way, waves goes, and they again focus here, contracts on the South Pole. So what's happening on the sphere? the waves are first spreading out. Here they go maybe on the south, maybe they will start from south. They all go out and then they go in here. And these points, North Pole and South Pole, are called singularities. Singularity. This is singularity and this is singularity. This is just mathematical. This is just mathematical term for saying that coordinates like meridians, right? They come here, to North Pole and South Pole. But actually, any points, any opposite points, may be used at North Pole and South Pole. If we're not talking about the real globe, if we have just sphere, all the points of the sphere are the same. Exactly. Sphere is symmetrical. So you can put like your South Pole here, and then, or South Prime, right? And then you will have opposite North Prime somewhere on the other side. And all the same thing. And when you start the waves here, they again goes here and contracts here. So they start spreading out and then inside here. Compare this, I'm talking to Antosha, and to you guys, if you remember, compare this with the lens. We were talking about the lenses some time ago.
The what, I'm sorry?
Optical lens.
Oh yeah, okay.
Optical lens. Optical lens do the same thing. It may expand the wave front or the lines of spreading the light, and then contract them to the focus. So this is singularity, or another way it is focus in a certain way. In the optical terms, it is a focus. So what's going on here? It's a very interesting point. When the wave goes out, right, from the south point, then it started going in. What happens in this point? It's a very interesting thing. The waves come here, and there happens something very interesting. We will have, this is like the surface of the pole, right? Here is the North Pole, right? And here are the waves which are coming, contracting out to the North Pole, right? This way, coming here, focusing on North Pole. They come from the South Pole. South Pole is down there, very far. They go and they start spreading, then they curved. This is a curved space, of course. You understand that the surface is a curved space. So it goes, and then they contract here. So it looks like what? That South Pole is repulsing point, and the North Pole is attracting point. You see, right?
No.
No?
What's the difference?
It started from South Pole. So the waves are like repulsed from it.
Okay, but if we don't know where it started, there is no difference between the two.
No, that's another thing. It's the symmetry but it started somewhere. You hit it in the North Pole. You hit it at a certain point, which is called South Pole. So they come to the opposite point, which is now called North Pole, right?
Yes.
So yes, there are any you can use any point, but and the sphere always do something like a lens. So it's do some interesting things with this fronts, the wave fronts, right?
But why do you say it's repulsing it if the waves come back?
It looks like no. They are repulsed from South Pole, but they are attracted like they look like attracted by North Pole.
But they come back from north back to south, do they not?
Wait, don't run ahead, ahead Pravos. Don't run ahead the locomotive. Don't run too fast, Antosha. Don't run too fast, okay? So it looks like it is. Okay, it looks like. Looks. Like S is repulsive and it's attractive. So it goes focus in the north. Now what happened next? When focusing on the north, you'll see interesting things. Very interesting things. That maybe I should this small think of the globe. This is north and this is south, right? And here are waves or whatever meridians, right? And what is parallels, right? These parallels are like waves. So if you see from this point of view, this circle, this wave is inside. This is outside, right? This is even more outside than this, right? They're relative, right? So this is inside, this is outside. This is outside of this. All that sort of things. So this looks like outside for this circle. If you look for the Flatlanders, again, we're talking about Flatlanders. If they see Flatlander is here, he sees this is outside for him, is it out, and this is inside for him, right?
Yep, I see
But
it.
when they come here, right? When they come here, another Flatlander for who is inside here, right? For him, this looks inside and this is outside. This is just about relativity again a little. So different Flatlanders, your inside house, everything is outside. If you are outside house, everything what is in the house, looks like outside from outside. So just think about it a little. So now what happens here? These waves are coming here, right? They're coming here. They superpose each other because nothing happens. They go to this singularity. They focus here. This is the maximum amplitude of the waves here. The wave come, and then it passes through. What is going on actually? So any movement that goes here, right, like this, exactly like in the loop, it goes easily through the north and goes here. So the movement of this wave, it goes through north and goes here, now this way. First goes inside and then goes outside. The same thing for the other. Any movement on this, any point of this, on this wave front, right? It goes to the pole like this, from this point to this point, from this point to this point, from this point to this point, from this point to this point. Something interesting is happening here, and you think about it. Think about it. One of the questions that I will ask about what is going on in here, and try to picture for yourself, because a very interesting thing is happening. So what is happening here? Happening here that something which was from position of north was in a circle, and this is outer circle, right? When it passes through the north, this circle, because it passes first, it becomes the outside circles now. You see, it passes first, it comes already here, and the second comes later, so it's here. So it becomes inside now. Just think about it. And this interesting situation is called change of orientation, because the orientation the direction was going this way, and then it goes out. When passed through this singularity point, the inside movement become outside movement.
So, question for you.
Yeah.
At what point does it become an outside wave? Does it inside wave? When it passes the Flatlander, or when it changes direction?
Say it again. There's no Flatlander yet, but okay. So what? Don't put Flatlander. It's
No.
make
You
complex.
said it was on the inside, now it's on the outside, or vice versa. Or maybe I misunderstood you. Okay.
I don't know what you're saying.
Okay.
I mean that this, okay, just the first point. This was inside circle from the north point. Flatlander, if you're talking from this guy who is sitting here,
Okay.
right?
Okay.
So this is like okay, maybe so not this guy. I'm sorry, because between two, right? So this was for him. It was inside circle. This was outside circle, right?
Oh, no. I think it's the other way around. Because it's relative to south, right? So
That's
the big
if you're talking about this, yes, you're correct. But now it's about this guy. We're talking about this guy who is here. He's not on the South Pole. He's another guy who is sitting here. For him, this is outside. This is inside, right? But when it goes through the pole, through this singularity point, right? What happens? This wavefront comes first. It passes through this singularity, right? Passes through it like this, contracts, and then starts expanding again. And it goes already here when this comes only to the pole. This only coming still here, and this guy already here. So going this way. So this becomes outside. The first one.
After it passes the guy. Not when it changes the direction, but after it passes the guy.
No, it's not passes the guy. This passes the guy later, but it doesn't mean anything. Like, I don't know how to say it another way.
Why does it become an outside?
When it passes, the guy is still there, right? The guy is still there. He's not going anywhere, right? In the moment. The wave's passing him, right? So this inside circle, it goes through the North Pole and then it goes expand, and to expand to this, it becomes this. And then this one comes to this position and then to this. And it becomes this when passing the circle. So this is why the singularity has this name. Singular means weird, like some weird behavior. So something very interesting and weird is going on in this pole, in this focus. And again, if you look here, this is the now two-dimensional surface, right? And again, the movement is that suddenly starts here, right? Then it comes here, it stops here, and then starts coming again. So velocity is changed. Here it goes with some velocity, then it's stopped, and then it goes back, right? So velocity changed its sign from plus to minus. And changes of velocity means acceleration.
Except it doesn't stop.
Yes, nothing stops. Again, I'm talking about that curvature. Look, it makes it looks like that there are changes in velocity, but there are no change of velocity or anything. Velocity, remember, I was talking about there's only one velocity, it's the velocity of light in actual reality. But when you see this, it looks like that velocity changes. It starts from some zero, then it accelerates, like repulsed from South Pole, then it stops again, then passing through singularity, it starts going back and all that sort of things.
It does not stop, that's what I'm saying.
Of course it's not stopping. Of course it's not stopping. I'm telling you.
It just switches the speed from positive to negative instantaneously.
No, it cannot. It cannot be done like instantaneously. If you change this thing, there's a not instantaneous. There's interruption and very strong. It's the speed was like here, and then it becomes opposite. It was plus v and it was minus v. So there is a point of acceleration.
Right, but it does not stop at any point, though, right?
It does not. Again, I tell you again, this is the whole magic of curvature. This is a paradox, sort of. The whole magic of curvature is that the speed is not changing. But if you look at it, it looks like that speed changed abruptly in this point. And the point is called singularity.
With infinite acceleration.
It is acceleration.
Infinite.
Oh, yes, almost infinite. But in the other case, actually, it cannot infinite. Yes. In the middle it is zero, you're right. There's plus v, then it stops. Here it's v0, and there goes minus v.
But it does not really stop. When you say stop, there's got to be some sort of appreciable a period of time at which it's not moving. But
that's why again, this is a picture. That's why it's called singularity. You may think about it. This is why it's called singularity. Singularity is about coordinates. It's not about real speeds or whatever. You know, in reality, it may look very differently, because when you change different coordinates, so different coordinate frames or frame of reference, the situation can look very differently. In these coordinates, like meridians and parallels, right, like our globe, it looks like that change is very abrupt. There's interruption. There's going, and stop, bang, back, like banging back, right?
Yeah.
So you may say about the waves that waves are actually reflected from this point. Actually, why we talked before about reflection, remember? It's exactly reflection. Here it is reflected.
It cannot be exactly
It is
Yeah.
bouncing.
So
It
does
is.
it,
It is bouncing. It is bouncing, Natasha. Think about it really, and just think about this. This is exact point of reflection. So it's a sort of a focus, like a lens, and actually it is a reflection of a certain way.
it certainly is not. It just each point travels right through singularity and continues to travel.
No, not continuous. Look, Antosh, easy to say. Easy to say. The wave was going this way, right?
Yeah.
Goes to this point and goes to quite opposite. It is
Yeah.
reflection. It is called reflection in normal normal language. So
But
it is.
imagine that the wave that's traveling is not circular, but an oval, right? As such,
That's another story. You can think about it. It's not a point of election. Yes, Antosha, I agree that there are lots and lots of things, right? Lots of things. By the way, I have maybe some for entertaining, right? About these waves that going out of the pole, right? That actually your granddaddy thesis, right? Thesis, you know this, the PhD, right?
Yours?
Yeah, my. It
Yeah.
was very close to the waves like this going through the globe, because I'll tell you. Just it's maybe interesting. There are waves. They're called gravity waves. It's not gravitational waves. There's a gravity waves in the atmosphere. They just then have this name. So we have the globe, right? And we have so-called auroral circle. You know where the polar lights are? Where the magnetic lines goes inside the territory near the poles.
That's electromagnetic.
You know auroral circle. You know this term?
No.
Where the you know aurora? What aurora means?
Northern lights.
Yes, northern, not northern. They are southern too. They
The cold northern lights.
okay. They're called northern lights, but they are in the south too. The same.
Aurora borealis.
Actually, it's not circle. It's actually oval. But anyway, so auroral oval, right? Here and here. So here at the height of about 100 kilometers, right? In the height in the atmosphere, they create a strong currents, electrical currents, which creates waves which are goes in the atmosphere like this on the heights about from 100 to 500 kilometers. It's actually almost space, but it's not space. It's called magnetosphere.
But please, what's the medium? Is it the air?
Medium is plasma. Magnetosphere, plasma, ionized gas, very diluted. It goes up to 1,000 kilometers and higher. So it's very diluted, and the waves actually have the amplitude of waves, the height, it goes up and down. The amplitude is like 300 to 500 kilometers high. That kind of waves goes there around the globe. Because of this, when the auroral lights goes, they create these waves. And the waves they go through the globe, and they pass from south, and here they go from both places. They interfere. They pass through the northern and southern singularities and go back, and they can circle like this, like reflecting like 3 times and more.
At what speed?
Speed is different, but it's pretty high. I forgot exact speed, but it's higher than the jet speed, the plane jet.
Would it be the speed of sound in that in there?
No. This is plasma thing. It's not sound. This is plasma waves. There's totally different equations. But anyway, just just a picture, just for you to understand. It's not just the talks about rubber membranes and everything. It's also it happens around us. And these waves were calculated. I calculated those. This was the point of my thesis. There are actually more to that because there are different structure in the oval and everything. It was taken consideration. But anyway, it was about like this.
Is there a lot of energy in those waves?
Lots, of course, lots. Yeah, lots. The currents here are much more powerful, more powerful than the lightning. Much more powerful. And then very high, and 100 kilometers height. So they create waves that actually circulate the globe. Can you imagine this? So the power is it's great power, right? It goes from both poles, they interfere here and then goes back and forth and all that sort of things.
Yep.
I can tell also how much time it took to me to make all these calculations. About 2 weeks.
Wait, 2 weeks?
Huh?
2 weeks?
2 weeks, yes. My thesis took me 2 weeks to make the real thing, but it took about a year to fill all the documents for the thesis. So, okay. So that's it. The questions, guys. So you understand at least how curvature connected with acceleration. There's very interesting things. It looks like there's no acceleration in reality, right? The speed is not changing. Speed is also always c, fundamental speed. But what we see, it's very different. It looks like acceleration and looks like forces because, by the way, remember this, I'm sorry. Remember the second law, right? That force, right? It is mass multiplied by acceleration, remember? Acceleration, as we saw, it comes actually from curvature. So this is actually the result of curvature. There is no change in speed. This is the curvature thing. What about mass?
But hold on. But
yes?
You keep on saying that there is no acceleration.
Yeah.
But you feel it. What do you feel?
What do you feel when you stand on the ground? When you stand on the ground, what do you feel?
Gravity.
Gravity. What is gravity? Gravity. That's what I'm saying. Gravity. It is. It's not acceleration. Actually, it is a curvature of space. It looks like acceleration, yes, and because it looks as accelerations, it is in the formula. It stands like acceleration. But actually, it is a result of curvature that the space is curved. And just one short word about mass, right? Mass is, the proportion, right, between force and acceleration, right? And acceleration is actually curvature, so this is proportion to curvature. So if mass is 1, like force is like 1a, right? If this is mass. If mass is 2, force is 2a, right? And the same thing. So what actually happens that there's no one loop of time, it goes like in many circles. And the amount of circles, it is called mass or rest mass. It's called rest mass. So it's number of circles. So it's still circle, but just like a solenoid or lots of threads, right? So just a short thing, just to say. So mass is connected with these lots of loops in one. Okay, guys, questions?
No.
No question. Okay.
Can
Then.
you repeat the stuff about the things?
Huh? Say it again.
Can you repeat the stuff about the things?
Yeah, right. Can I repeat the stuff about the things? Right. Okay, now are you ready to write questions, right? Ready?
Hey, you're not playing something. Yes, we're ready. Quiet. No, we're not. Okay, I'm ready now.
Okay, the first. Draw pictures. Draw pictures for step-by-step passing polar, like north, singularity, by Flatlander. What will happen with Flatlander when he goes into singularity? Try to understand. I just pictured what is happening with the waves, right?
Write down word for word.
Yeah.
What happened to Flatlander when he goes through singularity? That's enough. I'll remember.
Yeah, but step by step. So draw pictures for yourself to understand what is really going. Like first put like his maybe head, maybe leg.
Nothing will happen. This is so true.
No, nothing. Okay, maybe nothing will happen, but still, you should understand what is going on there, right? So actually, there are happening certain things, but just the more you understand, the more you understand more complex things. So try it. This is very, very, very important.
No, but maybe I don't understand the complexity here because to Flatlander it would be he wouldn't even notice he passed it and he'll just continue.
That's no. Unfortunately, unfortunately. Okay. Yeah. Maybe just maybe one thing. Maybe I missed one thing. Maybe you're correct. For the Flatlander, which it goes like Flatlander, right? Nothing will happen because there's no wave, right?
Yeah.
But okay, so we should add this. So this Flatlander traveling with the wave.
Oh, so he's sort of like wave surfing.
Yes, he right on the wave. What is going on when he is on the wave? He's a part of a wave actually. Not even surfing, but he's part of the wave. If the wave contracts, the Flatlander contracts. You know, something like this. So try to understand this. This is a very important point. You got it, right, Antosh?
Yeah.
Okay, you wrote the second one. This is for you, Antosha. Use to help children, right? Use optical lens rules. You know, graphic, how to
We did not study that.
tell them. I I told about it a little, but you just tell them. It's not that difficult. Picture how it goes. You know this parallel.
Yeah, I know.
Yeah. So use optical lens rules, not the formula, just the rules. You know how to put.
Yeah, I get it.
Use optical lens rules to find out what is happening with light Flatlander. Light means composed of photons. Flatlander.
This is called geometric objects.
Okay, geometric objects, whatever. Yeah.
Yeah.
But you speak to children that this is actually Flatlander, which is composed of photons.
Yeah.
He is a light creature. You know, not
Yeah.
light that no weight. He is composed of
Yeah.
light particles. Okay. And what happens when he passes through the lens? And compare this with the first, right? Flatlander goes through the focus. The focus. Compare.
Yeah. Second question is what happens to Flatlander when he travels through a lens or she?
Yeah. Electromagnetic Flatlander. So light Flatlander. Composed of photons. Now the third.
Hold on, Ted.
Yeah, okay.
I just write it down.
Sure. Mhm.
Oh, this is correct.
Use optical lens rules. That's actually geometric to find out what is happening to a light Flatlander when traveling through the not through the singularity, through a lens, through a lens. Just say through a lens, and it's not optical; it's geometric.
Okay.
Okay, good.
Yep.
Question 3. Again, draw pictures step by step for yourself, of course. Draw pictures step by step for a like circle. They call circle motion of a Flatlander on clay bottle surface.
A Flatlander on clay bottle.
On the clay bottle. Flatlander traveling along all this, all these tunnels,
Yeah.
right?
So basically, figuring out how from the inside he ends up outside.
Yes, right, exactly. It looks like, and try to point out what happens with his right and left hand. You know what you're talking about.
Have one clean bottle.
Yeah, exactly.
The same thing, you try to understand the same thing, maybe returning back to the question 1, what is going on with the Flatlander left hand and right hand when he passes through the pole, through the singularity. Just try to understand that. Okay. Any questions? Okay. Okay, guys. Have fun. Окей. Целую вас, люблю. Счастливо, ребята.